Deep beneath one of California's most iconic mountain ranges, the Earth is doing something scientists have theorized about for decades, but almost never been able to prove is happening right now. Part of California's crust is peeling away. It is sinking into the mantle. And according to the researchers who found it, the process is not finished. It is moving north. Today, we're breaking down exactly what's been discovered beneath the Sierra Nevada, how scientists caught it in the act, and why the direction this process is heading matters for the northern half of the state. Let's start with the basic science, because the concept at the center of this story sounds almost impossible until you understand the mechanism. The Earth's lithosphere is the rigid outer shell of the planet, the layer that includes both the crust and the uppermost part of the mantle beneath it. Under normal circumstances, this layer sits on top of the hotter, softer asthenosphere below it, relatively stable, relatively permanent. But there is a long-standing theory in geology called delamination, also referred to as lithospheric foundering, which holds that under the right conditions, the lower portion of this rigid shell can become denser than the material underneath it. When that happens, that dense lower layer can detach entirely and sink down into the mantle, like a slab of rock quite literally peeling away from the base of a mountain range and dropping into the depths below. This idea has circulated in geology for a long time, but concrete, direct evidence of it actually happening in real time has been extraordinarily difficult to find. Most of what geologists had to work with came from ancient mountain belts, places where a delamination event was believed to have occurred millions of years in the past, long since eroded and disturbed, leaving only indirect secondhand clues behind. What researchers have now found beneath California's Sierra Nevada is different. This is not an inference about the deep past. This is a live snapshot. The discovery comes from a team including researchers Vera Schulte-Pelcom and Deborah Kilb, who used a technique called receiver function analysis, a method that uses seismic waves passing through the Earth to build a detailed image of the structure hidden below the surface, essentially an ultrasound for the deep crust and upper mantle. Publishing their findings in the journal Geophysical Research Letters, the team identified a distinct, unusual layer sitting in the mantle beneath the central Sierra Nevada, a layer that corresponds almost perfectly with the predicted signature of an active, ongoing delamination event. This is not a cold case. This is a process caught mid-motion. Here's what they actually found, layer by layer. In the southern Sierra Nevada, researchers identified thin crust sitting directly above shallow asthenosphere, meaning the softer, hotter mantle material has already risen up close to the surface in that area, exactly what you would expect to see after the dense root of old lithosphere has already detached and sunk away, leaving a gap behind that gets filled in by rising material from below. This specific feature, known to researchers as the Isabella anomaly, has been studied for years and represents strong evidence that delamination already occurred beneath the southern Sierra, likely millions of years ago. But the central Sierra tells a different, more active story. There, the data revealed a distinct shear layer in the mantle, a signature the research team interprets as evidence of foundering that is happening right now, live, as the crust in this specific section of the mountain range continues actively separating and sinking. This matches earlier observations of unusual deep earthquakes recorded beneath Yosemite National Park and the surrounding foothills. Seismic events that occur at depths and with mechanical signatures that make far more sense once you understand them as direct evidence of cold, brittle lithosphere actively cracking and pulling apart as it founders into the mantle below, rather than flowing smoothly the way hot material typically would at that depth. And then there's the northern piece of this story, the part that gives this discovery its forward momentum. Researchers found no evidence of this same delamination layer beneath the northern Sierra Nevada. None. According to the study's authors, that absence is not simply a null result. It indicates that the foundering process has not yet progressed to that part of the range. But the data trend, moving from clearly finished in the south to actively in progress in the center, points toward a process that is spreading northward over time. This is the part of the story that I think deserves the most careful, honest framing, because it would be easy to sensationalize a phrase like spreading north into something it is not. This is not a fast-moving event. Lithospheric delamination unfolds over a timescale of millions of years, not months, years, or even human lifetimes. The researchers themselves describe this as catching a geologic event in slow motion, comparing it to witnessing the Earth's own long-term self-recycling process unfolding in near real time by geological standards, which still means an extraordinarily slow, gradual progression by any human measure of time. So why does this matter at all if the process is this slow? A few reasons, and they're worth walking through individually. First, delamination has real surface consequences, even on geologic timescales. As dense lithosphere detaches and sinks, hot asthenosphere rises up to fill the resulting gap, and that upward flow of hotter material can drive uplift at the surface, contributing directly to the elevation and shape of a mountain range over time. Some geologists have connected past delamination events beneath the southern Sierra to episodes of unusual volcanic activity in the region's more recent geologic history, since the rising asthenosphere, replacing sunken lithospheric material, can also trigger melting that eventually reaches the surface. Understanding where this process is active today helps researchers understand both the past and the likely future landscape evolution of one of California's defining mountain ranges. Second, and this is the piece with the most direct relevance to seismic hazard, active delamination appears to be directly connected to the region's pattern of unusually deep earthquakes. The cold, brittle nature of lithosphere undergoing this kind of active foundering gives it the capacity to crack rather than flow, and researchers have specifically linked that cracking behavior to the deep seismicity already documented beneath the Central Sierra and the Yosemite foothills. As the active zone of delamination continues its slow migration northward, seismologists studying this region will be watching closely to see whether that same pattern of deep seismicity begins tracking northward along with it, since a clearer understanding of where and why these deep earthquakes occur feeds directly into more accurate seismic hazard modeling for the broader region. Third, this discovery matters simply as fundamental science, independent of any direct hazard implication. Delamination is one of the processes geologists believe may play a significant role in how continental crust itself differentiates and evolves over deep geologic time, potentially helping explain how some of Earth's more evolved, lower-density continental crust actually formed in the first place. Getting direct, real-time observational evidence of this process actually happening, rather than relying purely on theoretical modeling or indirect ancient clues, represents a genuinely significant contribution to understanding how continents work at a planetary scale, not just a regional curiosity specific to California. Let's talk about what researchers are doing next, because this study is explicitly framed as an opening chapter rather than a closed case. The team has stated its intention to continue monitoring the Sierra Nevada region using a combination of deep Earth seismic sensors, computer simulations modeling how this foundering process should behave under different conditions, and satellite-based measurements capable of detecting extremely subtle changes in surface elevation over time. If the delamination process really is migrating northward the way the current data suggests, continued monitoring over the coming years and decades should reveal a gradually shifting signature, both in the deep seismic data and potentially in subtle surface uplift patterns, tracking that migration in progressively more detail. Let's go a little deeper on the method itself, because receiver function analysis is worth understanding on its own terms. The technique works by analyzing how seismic waves generated by distant earthquakes, sometimes originating thousands of miles away, change as they pass through different layers of rock on their way up through the crust and mantle beneath the seismic station. Every time a wave crosses a boundary between two materials with different physical properties, it produces a small distinctive signal, essentially an echo, that gets recorded at the surface. By collecting these signals from hundreds of distant earthquakes recorded across a dense network of stations spanning the length of the Sierra Nevada, researchers were able to build a detailed, layer-by-layer cross-section of the crust and upper mantle running the length of the range, revealing structural boundaries and anomalies that would be completely invisible using any single, simpler seismic measurement. This is fundamentally a technique built on patience and volume, stacking together signal from an enormous number of individual, faint seismic echoes until a clear structural picture finally emerges from what would otherwise look like noise. It's also worth placing this discovery in a global context, because the Sierra Nevada is not the only place on Earth where scientists have looked for direct evidence of delamination. Other regions around the world, including parts of the Tibetan Plateau, the Alps, and sections of the Andes, have all been proposed as possible sites of past or ongoing lithospheric foundering, based largely on indirect geochemical and geophysical clues. What makes the Sierra Nevada discovery stand out within that broader global research effort is the clarity and directness of the evidence. Rather than piecing together indirect clues about an event assumed to have happened deep in the geologic past, researchers here identified a structural signature consistent with delamination actively in progress, observed through a dense, well-instrumented modern seismic network, giving the global geoscience community one of its clearest direct examples, yet of this theorized process actually caught in motion. One more piece of regional context worth mentioning. This active zone sits not far from Long Valley Caldera, one of California's most closely monitored volcanic systems, located along the eastern edge of the Sierra Nevada near the town of Mammoth Lakes. The research team specifically noted that farther north, near the latitude of Long Valley, seismic data shows unusually shallow, low-velocity material beneath the range's high elevations, consistent with asthenosphere, sitting close to the base of the crust in that area as well. Long Valley has its own well-established history of volcanic unrest and periodic ground deformation, closely monitored for decades by the USGS's California Volcano Observatory, And while this new delamination research does not establish any direct causal link to Long Valley's known volcanic activity, the geographic proximity between an actively upwelling mantle signature and a historically restless volcanic system is exactly the kind of connection researchers will be paying close attention to as they continue refining their understanding of this region's deep structure in the years ahead. It's worth understanding just how long this specific question has divided geologists, because that context is part of why this discovery is being treated as such a significant breakthrough. The debate over whether the Sierra Nevada's unusual topography and geochemistry could be explained by lithospheric delamination stretches back decades, built originally on studies of volcanic rock samples and deep mantle fragments called xenoliths, brought to the surface by volcanic eruptions that gave geologists indirect clues about the composition of material sitting deep beneath the range. Researchers as far back as the 1990s proposed that a delamination event beneath the southern Sierra could explain patterns of unusual volcanic activity in that part of the range, but proving that theory with direct, unambiguous seismic evidence remained elusive for years, largely because building a seismic dataset dense and precise enough to actually detect an active foundering signature requires exactly the kind of extensive, modern seismometer network that has only become available relatively recently. This new study effectively closes a scientific debate that specialists in this specific corner of geology have been having for the better part of 3 decades, replacing indirect, circumstantial evidence with a direct structural signature captured in the act. Now, about that northward trend specifically, because it's worth being precise about what the data can and cannot currently tell us. The researchers are careful to frame the south to centered absent in the north pattern as evidence consistent with a process that has progressed and is continuing to progress northward over geologic time, not as a confirmed, precisely timed prediction of exactly how far or how fast that migration will continue. Extrapolating this kind of deep, slow-moving geologic process into a specific future timeline, predicting exactly when or whether this active zone might eventually reach the northern Sierra Nevada or the broader Northern California region, is simply beyond what current data can responsibly support. What researchers can say with confidence is that the pattern observed so far, fully finished delamination in the south, an actively ongoing process in the center, and no detectable signature yet in the north, is internally consistent with a genuine northward progressing process, and that continued monitoring over the coming years should help clarify both the pace and the ultimate extent of that migration with considerably more precision than is currently possible. It's also worth addressing directly how this discovery has been covered elsewhere, because some of the framing circulating online leans considerably more dramatic than the underlying science actually supports. Headlines describing California as peeling apart or tearing itself apart beneath our feet aren't technically false, but without the geologic timescale attached, they can easily be misread as describing something sudden, unstable, or actively dangerous in a way that maps onto human experience. It doesn't. Delamination is a process that unfolds over millions of years, and the version of it currently active beneath the central Sierra Nevada has, by all available evidence, been progressing at that same glacial pace for a very long time already. The genuine news here isn't that something alarming is suddenly happening. It's that scientists have, for the first time, obtained direct, high-resolution evidence of a process that has been theorized for decades, observed in a location and at a level of detail that was simply not achievable before this specific combination of seismic network density and analytical technique came together. That is a real meaningful scientific achievement. It is not, on its own, a reason for anyone living across California to feel a new sense of urgency about anything happening beneath their feet this week, this year, or even within their lifetime. It's also worth noting how this kind of discovery typically comes together, because it says something about the current state of Earth science more broadly. This wasn't the product of a single instrument or a single dramatic dataset. It came from combining decades of accumulated seismic station data, much of it originally deployed for entirely different research purposes, with an analytical technique refined over years of methodological development, applied by researchers willing to spend the time reprocessing and reinterpreting existing data through a new lens. That kind of slow, cumulative scientific progress rarely makes for a dramatic headline on its own, but it's exactly how a decades-old theoretical debate about the Sierra Nevada's deep structure finally got resolved with direct observational evidence. For residents across California, and particularly for anyone in communities near or north of the currently active Central Sierra Zone, here's the responsible, non-alarmist takeaway. This is not an imminent threat requiring any change in day-to-day behavior. This is a slow geologic timescale process that offers scientists a rare, direct window into how mountain ranges and continents themselves evolve over deep time. What it does reinforce is the value of the region's ongoing seismic monitoring infrastructure. Since the deep earthquakes connected to this process are part of the broader picture California's seismologists already track continuously as part of standard statewide earthquake hazard assessment. This story is a genuine reminder that some of the most significant discoveries in earth science aren't happening in a single dramatic moment. They're unfolding in slow motion, deep underground, revealed only through years of painstaking data collection and analysis. Beneath the Sierra Nevada, California's crust is quite literally being recycled back into the planet's interior, one slow motion piece at a time. And for the first time, scientists have a real-time, direct view of exactly how that process works. If you want to stay current on discoveries like this one, subscribe and turn on notifications, because we'll keep tracking this research as new monitoring data comes in over the following months and years. And if you know anyone across California with an interest in the deep science behind the ground beneath their feet, share this video with them, because stories like this one rarely get the attention they deserve compared to more immediate, headline-grabbing hazards. We'll keep watching the data, and we'll bring you the next update the moment there's something new to report.